Hi everyone, this presentation covers Chapter 12 on experimental studies in the third edition of Jacobsen's textbook, Introduction to Health Research Methods, a Practical Guide. In this chapter, you will learn that an experimental study assigns participants to intervention and control groups in order to test whether an intervention causes an intended outcome. Here's an outline of the chapter. Section 12.1 provides an overview. Section 12.2 covers describing the intervention. Section 12.3 covers defining outcomes. Section 12.4 covers selecting controls. Section 12.5 covers blinding. Section 12.6 goes over randomization. Section 12.7 covers ethical considerations. Section 12.8 covers efficacy. And Section 12.9 covers screening and diagnostic tests. This is a pretty dense chapter, and it's probably one of the longest presentations in this textbook, so bear with me. There's a lot of concepts to cover. Section 12.1 Overview. So experimental studies are considered the gold standard for assessing causality. They're usually called a randomized controlled trial. You may see them listed as a randomized clinical trial or RCT in general. So a controlled trial is considered whenever any time there's a participant that is assigned to an intervention group or assigned to a comparison group. So anytime people are assigned to these different groups, it's considered a controlled trial. A randomized controlled trial is when they're randomly assigned to these different groups. So you can have a trial where you assign people to different groups and then test a treatment, but it's not considered an experimental study unless they're randomly assigned to those groups. And so Figure 12.1 goes over the key characteristics of experimental studies. So what is the objective? To compare outcomes in participants assigned to an intervention or a control group. The primary study question could be something like, does the exposure cause the outcome? The population includes similar participants that are randomly assigned to an intervention or control group. So when do you think you would use this approach? You want to use an RCT or an experimental study when wanting to assess causality. A requirement is that the experiment is ethically justifiable. So some of the things you want to think about as the first steps include to decide on the intervention and eligibility criteria, define what will constitute a favorable outcome, decide what control is appropriate in comparison to the intervention, decide whether blinding will be used to prevent participants or the researchers to know the outcomes, and select the method for randomizing participants to an intervention or control group. Some things that you want to be careful of and you want to look out for are non-compliance, so there could be some high dropout rates, and a key statistical measure here is efficacy. Figure 12.2 goes over a framework for an experimental study. So starting off here in the first column, what exposure was the individual randomly assigned to? So individuals in the study could be assigned to the intervention group and assigned to the control group. Now from that, if you're assigned to the intervention group, then it could produce a favorable outcome, but it could also produce a not favorable outcome. Same thing with the control. There's two possible outcomes. It could be a non-favorable outcome or it could be favorable. So experimental study designs require careful considerations of the intervention given, the type of control and why it is appropriate, how participants will be assigned, the endpoint that is considered a favorable outcome, and ethical challenges associated with assigning participants to an exposure. Section 12.2 covers describing the intervention. So if you have a randomized controlled trial, typically you're comparing an intervention to a placebo or an existing treatment. An intervention is a strategic action intended to improve individual or population health status. And so interventions are used most often in prevention science. This is a scientific study of what preventive health interventions are effective in various populations, how successful the interventions are, and how well they can be scaled up for widespread implementation. So one of the first steps in an experimental study is to carefully define the intervention in terms of person, place, and time. So you want to consider what the intervention will be, the eligibility criteria for the participants, where and how they will receive the intervention, and then when, how often, and for what duration they will receive the intervention. Section 12.3 covers defining the outcomes. So there's some different types of trials within a randomized controlled trial. First, we have the superiority trial. This aims to demonstrate that new interventions are better than some type of comparison, not merely as good. So you're wanting to show that this new intervention that you're testing is better than the old one. Versus an equivalence trial is where you're aiming to show that the new intervention is as good as the previous intervention. So you're not so concerned with whether or not it's better, but you want to make sure it's as good. Versus a non-inferiority trial, which aims to demonstrate that a new intervention is no worse than some type of comparison. And so figure 12.3 just goes over these types of successes I just covered. And so when doing those types of trials, you have to have definitions of what better means. So what constitutes a favorable outcome for an intervention for the participants and for the study as a whole? And so these must be stipulated prior to the initiation of the study. And figure 12.4 goes over some examples of favorable outcomes. So this table provides examples with an intervention, the intended outcomes, a favorable outcome, an unfavorable outcome, and a favorable outcome specifically geared towards a population versus just an individual. So let's just look at the top one here. If your intervention is a new diet and exercise-based weight loss program, your intended outcome could be something like significant weight loss. But how much weight loss is good? So a favorable outcome could be defined as the loss of at least 10% body weight and maintenance of lower weight for at least 6 months. The unfavorable outcome could be defined as the loss of less than 10% body weight or failure to maintain that weight loss for more than 6 months. And then looking at it as a population level, it could be that the favorable outcome is the proportion of those who lose at least 10% of their body weight and maintain that weight loss for at least 6 months. And you're wanting to see that it's higher in the intervention group versus the control, because then you're showing that your intervention is improving that significant weight loss. Section 12.4 goes over selecting controls. So a control group can be many different things. The control group could be a placebo. So if it's testing a new drug, you could give them a sugar pill, or it could be, something that looks like what the actual drug is, so that they don't know that they're not receiving the actual drug. It could also be a current approved treatment. So typically this is called the standard of care. So if you're testing a new treatment, say for cancer, you still want to treat them, but you're testing to see if the new one is better. So if they don't get the new one, they at least get their current form of care. A control group could also get health education materials. So it could be that you're testing a diet and physical activity intervention where people come once a week to have some health education sessions, and then some guidance from somebody there to talk to them and do exercises with them. But then your control group may just get a pamphlet of that. So they're at least still getting the advice about health education, but they're not getting that added on component of the intervention. And so figure 12.5 goes over some of these examples, and these are pretty much what I just talked about here, but looking at the type of control here. So if we have a placebo inactive comparison, you could compare that to, say, an active pill, and then you would want it to be very similar so that people don't know the difference and realize that they're not getting the actual pill, because then it could affect your results. And so there's some different other comparisons here that you can look at on your own. Section 12.4 goes over more in detail in the second part of selecting controls, and really part of what you want to do, so not just select those controls, but you want to determine how much of the intervention is required. So if it's a health education intervention, it could be that instead of doing 2 sessions a week, 1 may be sufficient. If it's a new dose of a treatment, you may want to have a lower dose that is just effective enough to treat, so that you don't have to put potential harm to the participants for other side effects. And so some studies use what's called the factorial design. And the factorial design tests several different interventions in various combinations, but within one trial. So you may have a new drug, but one may have 5 milligrams of the active ingredient. One may have 10. One may have 2. And one may have 0 because it's a placebo. And so here's just some example approaches to the different trials in figure 12.6. So looking at this first section here, if you have just parallel arms, so this is just these 2 treatments, so you have an intervention here and a control here, and then you follow them and evaluate their outcomes. So this is the most basic design. A factorial design has the different components in it. So you may have a intervention 1 and control, and then you may have intervention 2 and then a control, then you may have both interventions, and then you may have just the control here. Versus a crossover design, which is similar to the standard parallel arms, except for you give the intervention first to people, and then maybe 6 weeks later you switch it, and then they receive the control for 6 weeks. And then those that start off with the control, then they receive the intervention for 6 weeks. And so although experimental studies sometimes include a control group of participants that are randomly assigned to maintain usual routines, this method is not always preferred. And so Jacobsen goes over the Hawthorne effect, and this is bias that could occur when participants in a study change their behavior because they know they're being observed. So you may tell people to do the exact same things that they would normally do, but because they're in a study, because they're being followed up, because they know that someone's watching them, they may actually behave better, or even worse, usually is better than what they would normally do. And so that's a type of bias that could affect your findings. When there are ethical concerns about withholding a potentially life-saving intervention from participants, it may be possible for participants to serve as their own controls. So if it's you want to have a before and after study, this is considered a quasi-experimental study. And this is not done just with traditionally experimental studies. This is done also for knowledge, attitudes, and skills that usually are done in cross-sectional studies. This is for any type of educational evaluation where you do a pre-post test. But a quasi-experimental study is a study that measures the same participants before and after an intervention, and then their before status is considered their control. And so I mentioned the or the crossover design in a couple slides back. This is where participants are randomized to receive the active intervention first and then the control, and then those that receive the control first then later receive the intervention. Sometimes studies have a washout period between those two arms because they want to ensure that the effects from the first treatment do not bias the results from the second treatment. And so this really is just a break between the two. And the carryover effects are those residual effects that they're trying to remove from that first part of the intervention so it doesn't bias the second part. Section 12.5 goes over blinding, and so blinding is often used in randomized controlled trials really as just a measure to reduce bias. It keeps participants and sometimes some members of the research team from knowing whether or not the participant is in the intervention or control group. Jacobsen goes over single blinding and double blinding. Single blinding is when participants do not know whether they are in active or control group. And double blinding is when neither the participants or investigators assessing the participants' health status know which participants are in the active or control group. So some of the other biases that may occur in this type of study design that you want to try and reduce if you're ever doing this type of study include information bias, reporting bias, and detection bias. So information bias is any type of bias that arises due to systematic measurement error. Reporting bias is any bias due to systematic underreporting of an exposure or an outcome. And detection bias is also called surveillance bias, and this occurs when a group that is routinely screened for adverse health outcomes incorrectly appears to have a higher than typical rate of disease because they have more frequent testing. So this enables a higher case detection rate in that population than would be if they were not normally screened. Observer bias occurs when the observer intentionally or unintentionally evaluates participants differently based on their group measurement. And so blinding is a way to help prevent that. And it helps the results be less biased because it prevents the observers from knowing the results of the people in the intervention group and the control group. So ways to minimize the risk of observer bias in studies that are not blinded could be to use objective outcome measures such as laboratory tests rather than relying on subjective outcome measures such as participants' self-reported feelings. Section 12.6 goes over randomization. So randomization, as we discussed earlier, is the assignment of participants to an exposure group in an experimental study using a chance-based method. So it mitigates any sort of allocation bias that may occur as a result of a non-random assignment. And so here you really are just trying to equalize the groups by randomly assigning them in different ways. And so some of those ways include single randomization. So this could be just a coin toss, a random number generator, or some other simple mechanism to randomly assign them to the experimental study or one of the groups. You could also use a stratified randomization, and this is where you put them in subgroups beforehand and then randomize them. It could also be block randomization, and here's where you put them into groups of people and then put the specific groups as an intervention or control. So it could be like clinics or schools. And so here's just an example of these different types of randomization. So simple randomization, each individual is randomized to one of the treatment groups. Then stratified randomization, here you have a block separated here and then randomized from there. And then block randomization, here is separated based on different characteristics. So everyone within that group is in the control, and everyone within that group is in the treatment. Section 12.7 goes over ethical considerations. So randomized controlled trials have the highest level of ethical considerations. Participants do not choose, and so they may have been unlikely to encounter what they, when they volunteer to be in the project, they don't actually know whether or not the study will help them. They don't know what they're receiving. And so what comes up a lot is the concept of equipoise, and this is experimental research should only be conducted when there's a genuine uncertainty about which treatment will work better. So once you get to the point of knowing a treatment is better than another one, then it's time to stop the study. Or once you get to the point of knowing that that treatment could be harmful, it's time to stop. So there has to be genuine uncertainty before continuing. And so that's why randomized clinical trials often have requirements for monitoring adverse reactions. And so here's where you would identify conditions under which the experiment would be discontinued, because you want to make sure it's stopped if an exposure proves to be risky, and if the intervention is so beneficial that it keeps the control group from receiving it, then that would be unethical. And so figure 12.8 goes over some examples of ethical issues in experimental studies by study stage, and it has some different example questions to ask. So we'll just go over the first one, and then you can go over the rest on your own time. So when studying or when selecting the study topic, you want to think about, is the study really necessary, right? So you want to make sure there is that genuine uncertainty. And is the experimental design truly necessary? So does it need to be a randomized clinical trial? Or can it be a study where there is some participation from the participants in what they receive? Are they able to select being in the intervention or the control group? And there are many things that can happen, particularly when you're getting into the clinical treatments. There could be an adverse reaction or an adverse event. And an adverse reaction is a negative side effect of a medication, vaccination, or other exposure, or other bad outcome related to the study. An adverse event is a negative outcome that may be a direct result of the exposure. And so these are all things that need to be considered and must be immediately reported to the appropriate IRB. So your ethical approval must include steps for notifying your IRB office at the institution and things that can be adjusted when you're finished. So section 12.8 goes over the concept of efficacy. And when conducting randomized controlled trials, you're looking for efficacy, which is the measure of success in an intervention. And this is calculated as the proportion of individuals in the control group who experienced an unfavorable outcome, but could have expected to have a favorable outcome if they had received the intervention, not the control. So a high efficacy is an indication that an intervention is successful. In order to calculate that, you will also need to calculate things like the number needed to treat and the number needed to harm. So the number needed to treat is the number of people who would have to receive a treatment to prevent an unfavorable outcome in one person. So you would have to treat blank number of people. You'd have to treat 50 people in order to have an unfavorable outcome in one of the people. And so a small number needed to treat indicates a more effective intervention. Now, a number needed to harm is in some ways the opposite. It's the number of people who would need to receive a particular treatment in order to expect that one person would have a particular adverse event. And so the number needed to harm indicates a safer intervention. And figure 12.9 goes over some of the calculations here for efficacy and number needed to treat, and it sets it up in the 2x2 table here. So we have on the top our outcomes, and then on the side we have our groups. So our A represents those with an unfavorable outcome in the intervention group, and B is a favorable outcome in an intervention group. Then C is the unfavorable outcome in the control group. D is the favorable outcome in the control group. And so if we wanted to look at the rate of an unfavorable outcome in the intervention group, we take A over A plus B. Then if we want the rate of an unfavorable outcome in the control group, you would take a C over C plus D. And then you're able to calculate your efficacy and number needed to treat based on these rates in the intervention and in the control group. So not only do we have efficacy, and these words are used interchangeably sometimes, but it's important to consider the differences. But efficacy is different from effectiveness and efficiency. Effectiveness is calculated with the same equation, but refers to the results obtained under real-world conditions. So when you're testing a new vaccination, a new drug, and people report the efficacy, then that's been done during the clinical trial. The effectiveness is what occurs once that treatment is more mainstream and more when people are in the real world and followed up. Efficiency is the evaluation of the cost effectiveness of an intervention that is based on both the effectiveness and resource considerations. And so the analysis can be done differently based on whether you're looking for efficacy or effectiveness. But you have two different types. You have a treatment received analysis or a treatment assigned analysis. A treatment received analysis is usually called per protocol. And this includes only the participants who were fully compliant with their assigned intervention or comparison protocol. And so this is used for calculating efficacy. The intention to treat analysis, however, includes all participants even if they were not fully compliant with the assigned protocol, and this is used for calculating effectiveness. So figure 12.10 goes over a flow of participants in an experimental study to show the differences in people dropping out and people being included in the analysis, and you can see that the numbers will be different based on how many dropouts there are. Then finally, section 12.9 goes over screening and diagnostic tests. So what is a screening? So a screening is a type of secondary prevention in which all members of a well-defined group of people are encouraged to be tested for a disease based on the evidence that they're at risk for the disease and early intervention would improve their health outcome. And so the goal of a screening or a diagnostic test is to compare two assessments, and they should measure the same thing. If you're trying to create a new screening test or diagnostic test, you want to compare it to a reference standard or a gold standard reference test. So any reference standard is a test used for comparison when examining the validity of a new diagnostic test, and the gold standard is the one that shows the actual prevalence of the disease in an affected population. When conducting tests of diagnostic accuracy, you also have to have a cut point or a threshold. And this is a value that divides a numeric variable into separate categories. So this is the cut point of where your test is being shown to be effective. Diagnostic accuracy is the percent of individuals who are correctly classified by a test as true positives or true negatives. And so this is the comparison with the gold standard to show that your test is as accurate as the previous version. And so ideally, the test should be as close to 100% diagnostic accuracy as possible. So then here's where the concepts of sensitivity and specificity come in, and you've probably gone over these in your epidemiology course. Sensitivity is the proportion of people who have a disease who test positive using the test, and the specificity is the proportion of people who do not have the disease who test negative with the new test. So an ideal screening or diagnostic test would have 100% values for both. I would say most of them would have a higher value for one or the other, but at least 67%, 60 or 70 up to 90 would be wonderful, but realistically not all tests are that sensitive and specific. Positive predictive value is the proportion of people who test positive with the new test who actually have the disease. The negative predictive value is the proportion of people who test negative who actually do not have the disease. So an ideal screening or diagnostic test, again, would have 100% values for both, but in the real world, that's not always the case. So figure 1211 goes over the calculations for each of these and has the actual status on the top. So this is through the reference standard, then your test results here. So those that are positive on the new test and the reference standard are the true positives. Those that test negative on the new test but test positive on the reference standard are the false negatives. Then we have false positives that are positive on the new test but negative on the reference standard. And then the true negatives are those that are negative on both. So sensitivity is true positives over true positives plus false negatives. Sensitivity is true negatives over true negatives plus false positives. That's specificity there. And then positive predictive value is true positives over true positive plus false positive. Negative predictive value is true negative over true negative plus false negative, and then your diagnostic accuracy down here is your true positives plus your true negatives over all of them. So with that, we have false positive rates and false negative rates. A false positive rate is the proportion of people who actually do not have the disease, who incorrectly test positive using the new test. A false positive rate is calculated as 1 minus specificity. False negative rate is the proportion of people who actually have a disease who incorrectly test negative using the new test. So an ideal screening or diagnostic test would have a 0% false positive and 0% false negative outcome. For tests with flexible cutoff points for defining positive and negative results, there's always a trade-off. So once you increase your sensitivity, it may decrease specificity. If you increase your specificity, this decreases sensitivity. So it's always a balancing game between those two. And so here it shows some differences in the testing level of the cutoff. So changing the cutoff for your threshold can change that sensitivity and specificity. So here we have the initial cutoff point misclassifies some people here. So if we have, these are our negatives, and then you have one person who's a positive but's in the negative group. Here we have a few more, and then here we have less. And so you can go over these different numbers here and see how, this lower number here, there are no false negatives, but then there are more false positives. Over here, again, you have more false negatives, but then you have no false positives. And so it's really a balancing act between the three here. So another way of looking at diagnostic accuracy is a receiver operating curve, and these are calculated by statistical programs like Stata and SAS. It's used to graphically examine the accuracy of the test, and it plots the false positive rate on the x-axis versus the true positive rate on the y-axis for different possible cutoffs. Then the area under the curve is calculated with a receiver operating curve. This is an aggregate measure of how well a screening or diagnostic test performs across various cutoff points, and it ranges from 0 to 1. So 0 indicates the test is incorrect 100% of the time, and 1 indicates the test is correct 100% of the time. So you want to have this 0.6, 0.7, 0.8, 0.9 area under the curve, which is a more valid result. Another thing that's used for testing diagnostic accuracy are likelihood ratio tests. And these are used in clinical settings and training for physicians. These are the probability ratios used to evaluate the accuracy in a clinical setting. And so Jacobsen has these calculations here for us here. So positive likelihood ratio test examines whether the new test is good at predicting the prevalence of the disease. So it goes a little bit further past number needed to treat and those epidemiology terms, and it looks more at predicting diseases. So a positive likelihood ratio is sensitivity over 1 minus specificity. And here you want to have a larger positive likelihood ratio. So it should be greater than 10, and then this would indicate a good test. The negative likelihood ratio test examines whether a new test is good at predicting the absence of disease. So here we have 1 minus sensitivity over specificity, and a smaller negative likelihood ratio, which is less than 0.1, indicates a good test. So that is it on chapter 12. I know it was a long one. There's a lot of information in this chapter, but I hope it's helpful to understand the concepts of randomized controlled trials and screening and diagnostic accuracy. Thanks for listening.